Welcome back to the discussion continued on the EM grids and supporting films. So far we discussed about the EM grids and we discussed about something about supporting films, what are the requirements of the materials, and also what are the types of the continuous films. So here we discussed about basically the two continuous films. One is a collodion, the other one is a foam war, and basically we have like a two different approaches of making the film. One is a droplet technique, the other one is the Valentine's method. So of these two, as we discussed in the last session, the stability of the film is more stronger when you are talking about the foam war films. Now let's move on to the next topic, that is the Holey films. So by now you know that the Holey films are composed of the holes of irregular shapes and irregular sizes at irregular positions. So let's now discuss about how to make the Holey films in the laboratory. So for those who want to don't stretch their arms or don't want to strain themselves, these can be available commercially. So the Holey films can be purchased commercially, and basically what I'm showing you here is a method where you can just create the Holey films in your laboratory by yourself. So what we do here is the form war again will be taken, and this is the concentration recommended for it. The 0.3 to 0.5% of the form war that is dissolved in ethylene dichloride is used for this. The same approach as we discussed in the last slide, this will be a microscope slide will be taken and will be dipped into this, and prior to completely drying of this, what we do is we just expose that microscope slide to the moisture. So now what happens for the continuous film, we let the foam war dissolved in ethylene dichloride to dry up in the open air. Thereby ethylene dichloride will evaporate, leaving only the foam war. The foam war will form a uniform continuous film on the microscope slide that was used in the last session for depositing on the electron microscope grades. Now what we do is between these two steps, before formation of the film, we expose it to the moisture. So the moisture, what it causes is it just makes or breaks the um, plastic film at several places depending on the exposure, and those breaks appear as the film, the holes. So what you are seeing here is a Holey film coated with a carbon. How to coat the Holey film with a carbon is the subject for the next slide. We will be discussing about that in a minute. So now the exposure to the moisture is a little tricky thing. So what do you use for the moisture is basically what we use, we don't go for, actually they suggest to go for a humidifier. The commercial people are always try to exploit the money from us, but this can be just set up in the laboratory itself. What can be done is just to take a kettle and just use an optimal temperature so that the water will be just coming out as at a slow fumes. So this requires some experience and some trial and error to see like what is the flow rate of the fumes that are water vapors that are coming from the kettle. So now if you just expose this foam war that is dissolved in dichloride to the fumes of the water vapors, that will be enough to just create these vapors. So what we do, we just take the foam war, the microscope slide, dip into the foam war dissolved in ethylene dichloride. Before it completely evaporates, we just swipe the slide only once onto the moisture and then let it dry. So it don't have to be stayed in the moisture too long. Too long exposure to the moisture will completely break the film, and too little will just leave you too small holes. So that means in order to have the optimal hole size and not to break the film, the exposure to the moisture should be at the optimal levels. So that means it should not be too much exposed, it should not be too short exposure as well. So and again, the moisture level should be at the optimal level. If the water fumes are coming out at a rapid rate, that can break the entire films. And if the water vapor are not at all existing, again that will not be enough to make any holes at all. So that means this is really a play between the moisture level and the rate at which you just swipe the slide before it evaporates. And again, there should not be any gap between the film, the microscope slide dipping into the solvent and exposing it to the moisture. So that means if there is a too much gap between these two stages, the film is already formed and the exposure to the moisture is of no use. So you have to be coordinate all these steps. So that means before start of the experiment, you have to make everything ready. The slide should be ready. The solvent should be ready, the moisture at the optimal level should be ready, and these should be at close proximity so that the transfer of the slide from this to this is minimized. So all this, even though this looks like a very tedious job, if you are careful enough or skillful enough, you can just manage it in no time. This is all like it just goes in a flash of a second. Dip it, expose it, and just take it away from the moisture so that the film will be formed. So even though just I took like a so long, the process is dip it, expose it, and take it out. So it just goes like within a second. Okay, so now the next question comes, where the Holey grids find the applications. As I said before, this is used for the alignment. So what is this alignment means? It is in the stigmation, correcting the astigmatism. How exactly it will be done? When you take these holes into the microscope, and especially when you are doing the stigmation, this is the case I am talking about in the absence of the FFT. If you remember, FFT will show us the diffraction rings. If you don't want to just depend on the diffraction rings, and if you want to just look at the view of the microscope and then decide whether the stigmation is done properly or not, this Holey film will be of helpful to us. Now in such case, how it can be done is just look at the any hole of considerable size, and if there is a stigmation present, the fringe around it will be asymmetric. So asymmetric fringe will tell us the presence of the astigmatism, and continue the stigmation process until the fringe around it will be symmetric in nature. So this will help us a lot and make our job of doing the stigmation much easier. So that is one application of the Holey films. And the next one is the cryo-EM experiment. Of course, this grade will be used in cryo-EM experiment for screening. So where exactly the cryo-EM experiment is useful? So now for this, I will take a small break here from the Holey films, and I will give you a small narration of how the cryo-EM works. So the cryo-EM is the strength of the cryo-EM is where the image of your protein or macromolecule suspended in its own buffer environment. So here, if you just look at the film here, there is a hole. The hole means there is nothing here, and everywhere else there is the plastic. On the top of the plastic, we just coat with the carbon here. So we have a place here where looks like a well, and we have a place where there is a substrate available. So now if you just send the protein has a chance of just sticking onto the substrate here, and some of the protein is trapped into the well. So because it is just looking like a well, just imagine if you spread the water, the water will just stagnate on this place and just accumulate into the well as well. So now our protein in a buffer is looking like a water. There will be some protein stuck onto the carbon surface and some protein trapped into the well as well. So when in this arrangement, when the entire the Holey film is frozen, then the protein that is just trapped in the well in its own buffer condition will be frozen. So now if just look at this protein that is just trapped into the well, the protein is in its own native environment, not making any contact with the substrate, but was just embedded in the ice in the conformation of its own choice. So if you just look at this arrangement, any protein that is trapped here and frozen will reveal us the true or the native conformation of the protein, and any analysis of this particular view of it will reveal the native conformation of the protein. So that is one and unique advantage of the Holey film. And as I said, because of the irregularity of the shapes, this will be confined only to the screening of the cryo-EM experiment. But if you have patience enough, you can just keep on just searching for the holes of meaningful sizes and can take the images. And this only prevents us to go from the not to go for the automation. So if anyone has the patience enough to just record by just screening to the valuable or meaningful holes, this Holey films still serve us as a better alternative for the cryo-EM experiment. So that's about the Holey films. Just a quick summary: Holey films or again a form of film, but the form of film is pre-exposed to the moisture so that the holes will be formed. Since the exposure is not in our control, the holes that are formed here will be of irregular shapes, irregular sizes, and in different locations. And this has the applications in the stigmation process and the cryo-EM experiment. Now we'll discuss about the carbon coated on the plastic films. So first question comes, why we have to use the carbon coated on plastic films? As you know, the plastic films has the least absorption. ADSO or PTION absorption. Absorption is a phenomenon related to the stickiness of the protein. So if the protein is not able to make a firm contact on the plastic film, that will compromise on the stability of the sample on the plastic film. So in order to improve this, some people will prefer to go for the carbon coating on the top of it. So carbon coating being rough in nature, that can give us a better absorption to the sample. So that's the reason why we go for carbon coated plastic films. Some people, instead of having the plastic film, they prefer to have the carbon coating alone on the straight copper grade. So that means the plastic film will be replaced with the carbon coated, and this is the case especially when they go for a continuous film. So especially when there's a continuous film, they prefer to go for carbon coating. As I said, this is always an individual choice to choose between a mere carbon coated grades or a carbon coating on the plastic film for your experiment. So that's individual choice. And the one advantage of the plastic film, to have the plastic film, is that will add more stability to your sample. One disadvantage of having the plastic film on the underneath the carbon coating is it increases the thickness of it, thereby reduces the resolution. So that's a play between stability as well as the resolution of it. So this is always like, so we always just see the plus points and minus points of it. Now let's move on. Whether you like the plastic films or not, we are going to discuss about how to have a carbon coating here. So this is the setup of the carbon coating. So this is basically a small vacuum setup. You can see a ball jar here, and there is a small stage here on the top of which we can just lay down our grids. And now what you can see here is a set of electrodes. The electrodes are made of the carbon rods, and these are powered by the power supply here. So the setup here is, we just evacuate the entire vacuum chamber, and we just let the air to be in the lowest, no, the carbon, take it back. So it is just only the vacuum, and when these electrodes are just electrified with the power supply, there will be a discharge between these two, and that will release the carbon atoms, and the carbon atoms will start sedimenting on the copper grids here. So that depends on what grids you are just placing here. If you just place a bare copper grids here, you are going to get the copper grids with the carbon coating on it. And if you place the copper grids coated with a plastic film, what you are going to get is the copper films with the carbon coating on it. and especially is the case when you use a copper film grade with the Holey film coated on it. That is going to give us a beautiful experience where the presence of the film will just accumulate the carbon coating and the wells will not accumulate the carbon film. So that means you are going to see a clear difference between a continuous film and the well. So that's about the having a carbon coating. Then here I said a carbon coating of 3 to 5 nanometer thickness should be good enough for most purposes. So remember this 3 to 5 nanometers in addition to thickness that is the plastic films provide. So that's the reason I said it is individual choice to choose whether to include the plastic films or the carbon coating. So now the next question comes, how do we decide whether 3 to 5 nanometer carbon coating is really achieved or not? For that we have some sensors here just placed around the carbon deposit, the copper grades, and that will be sensing what is the thickness of the carbon layer that is deposited, and you can just monitor this, and you have to power off just before it reaching. Let us say if you want to have 3 nanometers, you have to switch it off when it reaches 2 nanometers, because even after switching off the power there will be continuous depositing of the carbon coating on it. That will add additional 1 or 2 nanometers. So the next question comes, how much the confidence we can have between the thickness that is sensed at the sensor and the copper grade. Let us say if the sensor is placed somewhere here, just I am just giving an example, and you are just monitoring the you are monitoring the thickness of the specimen, the carbon coating here, and your copper grades are laid here. So how sure are you that the thickness monitored here will be the same as the thickness deposited here? So there may be some difference between these two, and this is one of the disadvantage of going for the thickness monitored. For this we have an alternative. So what people usually do is, of course this is off the record, and this can be just used by placing the lid of a plastic bottle here with a wax coating on half of it. So then don't ask me where the wax is coming from. Your human skin is the best source of the vaccine. Just use your hand, touch your nose, touch a part of your plastic lid and place it here. Now when you continue the experiment, when the carbon film start depositing, the place where wax is applied will prevent the deposition of the carbon film, and the place where the carbon film the wax is not applied will start accumulating it. So that means you have a contrast between a carbon coated and carbon free surfaces. By looking at the contrast between these, you know the carbon coating will give you a gray scale. By experience, you can just look at the optimal grayscale, and you can stop the experiment whenever a required gradient of the grayscale is obtained here on the copper lead. So having said that, then the good laboratory practices. So once all the experiment is done, before you leave, remember the carbon film is not just deposited on your grids alone, it will be just deposited everywhere else. So before taking away your grids and walking away from the instrument, it is your responsibility to clean everything else and leave the ball jar and the surroundings inside this ball jar in a clean shape. So it is not just use the carbon film and just go away. You need to just clean up the everything so that it will be useful for the next user, who knows the next user may be you yourself. So instead of just cleaning at the beginning of it, it is always just better to clean at the end of the experiment, so that the next user will start his experiment with a smiley face. So that's about the carbon films. And the next part what I have not shown here is the glow discharger. Let's spend some time on the glow discharger. Glow discharger is the one that just creates some ionic centers on the carbon film. For that we need to understand what is the carbon film will does to it. So we know that the carbon film is hydrophobic in nature, and we also know that the all the proteins or all the viruses that we work on are suspended in the buffers. The major constituent of the buffer is the water. So that means now we have two components in hand. One is a carbon film which is hydrophobic in nature, and the other one the protein suspended in the water. So they are the best friends. The water and the hydrophobic surface are the best friends. So what happens whenever you try to just put the specimen that is suspended in the water onto the top of the grid, the carbon, the hydrophobic nature of the carbon film will repel it so that it will not stick onto that. Then, will that not compromise the entire experiment? The answer is yes. Then how do we overcome it? That is by just for temporarily suspending the hydrophobic nature of the carbon film, and that will be done by the glow discharger. So what is a glow discharger is? So this electrode setup that you are seeing will be just replaced with a coil of the metal, so that in an optimal vacuum condition with a slight leakage of air, there will be electrons flowing from here. So the electrons that flow from here to here will just bombard on the carbon surface, thereby creating the charge centers on the carbon. This presence of the charge centers on the carbon film will temporarily suspend or nullify the hydrophobic effect. So these charge centers will just accumulate or just allow the water to deposit on it, and that will be helpful for us to take the experiment forward. So most of the times the carbon coater and the glow discharge will come as a package. So in the same instrument both will be accommodated. Only thing is these electrodes will be replaced with a ring here for glow discharge experiment, and that ring will be replaced back with the electrodes for the glow discharger. So the same setup will be used for either the glow discharger or the carbon coater. The next precaution that has to be followed is the freshly glow discharge grid has to be taken for the experiment. That means, yeah, I did the glow discharger today, and can I use it tomorrow? No, because the charge that is just accumulated on the carbon surface is transient in nature, that will last over time. So that means typically between 15 to 20 minutes it has to be used up. So once you do the glow discharger, the grid has to be used between 15 to 20 minutes. And another precaution that has to be followed is once glow discharge is done, this carbon grid, the copper grid with the carbon film that is glow discharge is acting like a magnet. So once a glow discharge is done, it has to be taken straight to the sample preparation. It should not be exposed to anywhere else. Even by accidentally, if it just goes out of your hand and just falls on any other surface other than the sample, it starts attracting them. So that means what you are going to see in the microscope is not your sample but everything else. So you have to be utmost careful in protecting the grade before doing the sample staining and the glow discharge, between the glow discharge and the sample staining. So that is the precaution. And by any chance if you sense that the grid was in contact with anything else other than your sample after glow discharge, it is better to discard that grid and just start afresh another experiment instead of wasting the time taking to that contaminated grid to the electron microscope experiment. So that's about the carbon coater and the glow discharger. Carbon coater will have electrodes, the carbon electrodes and the copper grids here, and the electrons, the carbon that is coming from here is sedimented on it, and by monitoring the thickness on it either here or with our in-house technique, you can just monitor the thickness of it and you can stop the experiment. The same setup can also be used for glow discharging. The purpose of the glow discharging is basically to minimize or nullify the hydrophobic effect of the carbon film. Thereby you can use the hydrated samples or the samples suspended in the water. So again we will revisit this concept of the water in the later stage, because if you recollect, with a great pain we have just dehydrated the specimen in the earlier stage, and now we are talking about the presence of the water here. So that will be addressed when you go for the staining process. So that will be the next set of presentations that I'm going to release in the YouTube. Thank you very much.